Thank you for the introduction, Audrey. And I'm very happy to see quite a few participants, I believe very young students who are joining this course, I think for the fourth time running now. So
Yes.
just to continue with your brief introduction, I mean, this course has been a very successful one, and it was prepared at the time when we were closed behind doors due to COVID. But we still managed to prepare it, and when COVID was over, we managed to start delivering it 4 years ago. And this is the fourth time that we are running it. And if you chose, the fact that you chose to follow this course, I think you will realize at the end that you have done a very good choice. I have the task of convincing you that you did the right choice with this first lecture. The idea behind the first lecture is to introduce you to the concept of the value of data, of why you need to be proficient in handling data. Let me first of all share my screen, because I won't be just speaking. I will be, of course, sharing with you several slides. First of all, can you see my screen?
Yes.
Yes, Aldo.
Let me go to presentation mode. Reduce this. So yes, the title of this presentation is Data and Operational Oceanography. I will, of course, explain exactly what we mean by operational oceanography and beyond. And also, I must say from the beginning that I know that I have a spread of different participants with different capacities, different backgrounds. So I will be going into some detailed explanations to beginners, because I would like to ensure that everybody follows and that everybody gets the value from not just this lecture, but also from the others that will come after me. But I already agreed with Audrey. Please do speak up if you have, while I'm explaining and delivering explaining the slides, if you have any questions and things to mention, please do write them on the chat, and Audrey will highlight to me in case I need to intervene and address some particular question, okay? But I was saying before, you did the right choice. Why? Because you know how much data has become important, not only in science, in management, in business, in finance, in many other applications. And handling data, being able to understand data is like a language. This is why we speak of data literacy, because data is about reading, communicating, and working and networking with data. So it's basically like a language. And we realized when we were preparing this course, we realized the need as lecturers meeting our students, especially those who are doing research projects and their PhDs and undergraduate projects. We realized that sometimes, not sometimes, almost always, students are struggling to learn the tricks, to learn the capacity of handling data. And very often they were doing it by experience. And we thought, no, we need to have a course which can support them. It's not enough to learn by experience. We want you to be professionals. And therefore, we want to deliver to you the best we know from our end about handling data. And this is indeed the heart of this course. I will be, of course, sharing with you all these slides. My intention is to make them available even as a PowerPoint, because I would like you to use them as much as you wish. There is no restriction on what, of course, these slides are also made up of various inputs which have matured during the years, but I've always believed of sharing. In fact, this is one of the main important messages that we want to share with you, that whatever you do is not only for yourselves, but also as a process delivering knowledge to others. And we speak very much about open science, and this is the trend today, to really share what you do, because this is how we can progress further and faster in whatever endeavors we do in research, by sharing our achievements, building on the past, and preparing for the future. But coming back to the slide, I need to say a few words, because perhaps it's not evident that data, when we speak of data here, you may be coming from scientific background, but data is not necessarily only ocean parameters, temperature, currents, salinity. Data goes much beyond. And in fact, we can speak about data regarding assets, data regarding operations, that is everyday activities, not just the ones we do on a personal basis, but the operations done by a company, by a stakeholder, by responsible entities, data on their performance, data on logistics, such as in shipping, but also in many other aspects. So please open up your mind. Data is not only about science. There is also non-scientific data. If you want an example, in fisheries, for example, it's not just about research, but it's also about measuring, for example, where the fishermen are going, which kind of fish are they catching, and from where, and which kind of boats and equipment are they using. You know, that this is also data, and this is also part of assessments that need to be done. So it's not just about oceanographic data that we speak here, and the tools that we apply for oceanographic data analysis is in fact basically also useful, and the same tools that are used for data in other areas. So this is one of the first things I wanted to speak about, okay? I hope that you are putting down some notes about what I'm saying, so that you really take advantage of all this knowledge that we will be delivering to you. But it's important then you will not find these things anywhere in books, okay? So please take the advantage and take the notes. I'm speaking rather slowly on purpose, so that you have the time to also jot down some notes about what we are discussing, okay? So this is the first important point I wanted to make, about the fact that data is not only scientific data. Also the aspect that data can be static or non-static. What do I mean? Let me give you an example. Let us take the example of an unmanned car, an automated car. You know, today people are speaking about automating almost everything, but also in providing a car that can drive you without looking. Okay, I mean, but what is essential for this kind of achievement? For what is this? What does the system that drives the car need? First of all, it needs to have some basic data. Data about where the streets are, where the pavements are, where the zebra crossings are, where the traffic lights are. So these are basic data which are always there. Okay, they may change, and you might need to update the baseline data. This is what we call baseline data. The data in the background, which is almost, which changes only gradually. But then there is also the operational data, the real-time data. If there is a person crossing, if there is a crossroad with cars going across, if there is a car moving parallel to you, faster or slower, these are all real-time data which the automated car would need to take into account in order to decide where and how to go. So I think with this example, you get an idea of what I mean by static and non-static. Static data is therefore the baseline data, which practically changes only slowly and can be updated from time to time, but is basically the same. But then the non-static is the real-time data, the data which you need on the spot to take decisions, okay? And I think this is a good example to understand that there are these type of data, static and non-static. And then I also add here in this slide, spatial or temporal, because as I'll show you with other examples during my lecture, I mean, when you look at data, let us stick here to data related to the sea, but you can view data in space so that you can view the patterns and the differences between one area and another. But you can also look at data in time of how the conditions of the sea and the state of the sea is changing in time. But this applies again to all other categories of data, in the sense that you can identify changes in space, but also changes in time. And therefore, data has to be analyzed in both these two dimensions, okay? In the dimensions of space and the dimension of time. So with this slide, I hope that I have widened your understanding of what is data meaning here, and what different types of data are we speaking about. And now I go to more on marine, on oceanography. And I start with this slide explaining to you the meaning of operational oceanography. You may have already heard about this term. You may not have heard about it, but basically, when we speak about operational oceanography, we intend making measurements at sea, which are not necessarily only for research. This is more than research. We are here speaking about collecting data in order to provide service, to provide support to a wide range of users. And I will give you in the next slides some examples. Very often, this means that the data which we collect has to be delivered to the user very soon, as quickly as possible in real time. And this is one very important aspect of operational oceanography, namely using many different tools to measure the sea from space, from in situ measurements with observing platforms, with numerical models. But the main intention is to deliver these data and added value to the users who need some particular information. And this is why we speak of data services, of dedicated data service, supporting conservation of biodiversity, forecasting and management of risks, and emergencies at the coast and at the sea. I will give you some examples so that you understand me. These coming slides are examples of where operational oceanography, where real-time data becomes essential. And I'm showing here a ferry boat in distress, reaching the harbor in a very bad time when the sea is very rough, and finding difficulty to enter into the harbor. First of all, we know that today there are the means to anticipate sea conditions, and a ship like this shouldn't have ever been caught in such a situation in the first place. But if it happens, we need to be prepared to tackle such a situation, okay? And in the past, the skill of a harbor master was very essential. Doesn't mean that it is not also today. But you know, today the skill of a harbor master is not enough. The harbor master must have the tools available in order to give the supported decisions. And these tools are very much based on using the available data also using artificial intelligence-based tools and technological solutions to provide intervention and taking decisions in these kind of situations. This is only one example, but we can speak of many different examples where we need to intervene with a decision that can be very, very important. And today, people can be sued if they do not use the appropriate tools in order to address these kind of situations. So we need the professionals need to be trained in order to be able to base their decisions on data. Another storyline. I'm showing you a few examples of where operational oceanography and the delivery of data. I'm taking examples related to the sea here, where operational data is very important. I'm taking the example here of an oil spill. The spill has been detected by satellite, and of course, the authorities need to assess, is this going to impact the coast on Malta or on Sicily? This is southern coast of Sicily, and this is the part of the Maltese Islands. And there is a threat, okay? There is a threat, and the authorities need to find out whether this threat will actually have an impact on the coastline. And this is where data is necessary, in the sense of acquiring whatever data is available in the area. We know that in this area, in a past project, we've set up an HF radar system with radars on the Malta side and on the Sicily side, providing operational information on currents every hour. But not only, using models in order to be able to predict where an oil spill would move and how its content will impact different parts of the coastline, with what intensity. And there are these tools, okay? These are all operational oceanography tools, which are based on data coming from satellite, from measurements, and from the application of models. And therefore, this is another example of operational oceanography in action. Another example here. Another example related to search and rescue. Okay, I'm showing here the Maltese Islands. This is a map of the Maltese Islands, and we have a call of distress. Okay, we have a call of distress of a boat without crew on it. So apparently the persons on it have been are missing and stranded at sea, and there is a call for search and rescue action. And this is quite a complicated activity. In this case, it is the Armed Forces of Malta who are responsible for these kind of interventions. But of course, they need data in order to understand where to go. Because, of course, with the big extension of the sea, you need to have the appropriate tools to help you pinpoint the best area where to go in order to do your search. And this entails doing some assessments, because you do not know when the persons on board have been in the sea. And therefore, you need to track the previous positions of the boat, 3 hours before, 6 hours before, and taking into account that the incident could have happened in all this time span. And depending on the time span, depending on the previous positions of the boat, one would then use models to interpret how the persons at sea would have floated in the meantime, and therefore being able to provide a search and rescue area where the operators, where the AFM, the Armed Forces people would go to do their search in order to narrow the area of search and rescue, and therefore being more efficient in finding and possibly saving lives. So another example where data on the spot is essential in order to intervene. Another storyline, this is an embayment, a yacht marina. The berthing spaces in black are those which are already in place, but there is a plan of extending. And of course, one has to do a lot of assessments because we need to do assessments on the wave impact, on the new installations, on whether these new installations will change the circulation in the embayment, whether we are exceeding the carrying capacity of the embayment, and quantifying risks. And this is an assessment which has to be done. But of course, it cannot be done without data. And therefore, it is about looking at what are the forcing factors in the domain and in this embayment, and therefore how knowing all this knowledge can allow you to make decisions whether this development, this addition is feasible or not. Another storyline, we want to do an assessment on possibly using wave energy for electricity around the Maltese Islands. We know that renewable energies are very important, and one option which one could consider besides wind turbines is to also use the wave resource potential. And of course, in order to start planning, you need to do some feasibility studies in order to find out whether the wave energy is sufficiently strong enough to make this activity feasible, even economically feasible. And again, you need data, you need models in order to understand whether this is possible. But also monitoring, long-term monitoring. I wanted to also include this example here. Long-term monitoring on many different aspects, like sea level variability, state of health of the coastal sea, impacts of climate change, global ocean warming, checking environmental impacts. There are so many different kind of aspects that one could assess. But of course, at the end, you are always looking at data. You need also always to make your assessments not qualitatively but quantitatively, and therefore being able to use data. In this case, I'm showing here. This is rather old now, but you can find a more updated version of how much are the oceans warming up, and this is the result of an ongoing. I won't go into the detail, but I'm showing here a slide of the Argo program. You can look up on the internet. You have the URL address here. But looking yesterday, this is the most recent map. This is an initiative between a large number of countries using floats, which are able to profile the oceans. And until a few days ago, on 8th of March, there were 4,159 floats operating in the oceans and collecting and delivering data. And this is how these kind of drifters do profiles and drift for a few days and then do the successive cycle of data reaching the surface and then transmitting the data by satellite. But I mean, just to mention that these assessments are based on data, and you need to have the appropriate platforms and the appropriate tools and sensors in order to collect the data. And we can go into a more wide aspect. I mean, marine policy and planning and decision making and maritime spatial planning is all based on data. I've given you a few examples of, and I hope I have convinced you of how much data is important in this aspect related to the sea, but not only. Now this slide, I think it's interesting because, okay, we mentioned that we need to measure the sea, but how difficult is it? to measure the sea. And I am showing you here on the left-hand side here, watching on how the weather is expected to evolve in the coming days in order to plan also our activity. But what I want you to concentrate here is to look at the patterns. These isobars, these isolines, these are lines of equal pressure. And as you know, they allow us to understand where we have the high pressure systems and where we have the low pressure systems. But what I want you to concentrate upon is on the size of these systems. Can you see the size is very large, of the order of 1,000 or 2,000 kilometers. And therefore, the atmospheric processes are large scale processes. When we compare to the sea, this is something similar. On the right, I'm showing you. This is coming from satellite data, okay, over a number of years. But it's showing here altimetry. Altimetry is measuring the sea surface level. Many people believe or think that the sea is a flat, except for the waves, is a flat surface. Whereas in reality, it's not. In fact, this picture is showing us how from satellite we can measure the sea level. Red is higher sea level, and indigo and black is lower sea level. So as you can see, at any instant, we're focusing here on the Mediterranean scale, but this is the same in all the other oceans. And you can see that the sea surface is full of bumps and depressions, bumps in red and depressions in blue and purple. And these changes in sea level produce currents, are related to currents. Where we have elevated sea level, we have clockwise anticyclonic, that is circulation. Where we have low sea levels, we have anti-clockwise cyclonic circulations. And therefore, what I'm showing here is how the patterns of the sea level in the sea are much smaller scale compared to the atmospheric. This means, and this is what I want to explain here, this means that measuring the sea is much more difficult than measuring the atmosphere. You know that with the atmosphere we have meteorological stations. In Malta we have one. In other countries there may be 2, 3, 4, but very few. But that is enough, because the systems are large scale, and we can have a few measuring stations and still be able to outline where the features are and how are they evolving. In the sea, being so much high resolution, patterns are much smaller scale, I think you realize that there is a difficulty, in the sense that we have to do measurements much more densely spaced, so that we need to do we need a much larger effort to be able to map the variability in the sea. The spatial variability in the sea is, but also in time, is changing continuously, and the scales are much smaller than in the atmosphere. And then there is the complication, of course, in the sea of the biochemical cycles and the relation to living animals and organisms in the sea. And of course, understanding all these intricacies becomes really overwhelming. But again, it is about collecting data and interpreting data. This is showing what I was explaining before, but with a focus on the Balearic Islands. I like a lot this video, and I wanted to show it to you. But the animation is showing this is again sea level, okay? Sea level with red, higher sea level, and indigo and pink, lower sea level. But as you can see, there is a lot of what we call mesoscale patterns. And all these patterns are associated with currents, as I was mentioning before. Where there is a high sea level, there is clockwise anticyclonic circulation, whereas where we have reduced sea level, we have an anti-clockwise, a cyclonic circulation, and therefore showing you here in more detail what I was saying before, namely that currents are very much related to these structures, and that these structures are very much small scale compared to the atmosphere, and therefore this increases the difficulty of measuring and understanding the sea. Okay, this cartoon is again reflecting, therefore, on what we need in operational oceanography. If we want to deliver to our customers, to our users, the best information, okay, we need to measure the sea in the many ways possible that we have available. And as I'm showing in this cartoon, the observing system is composed of many elements, with seabed instruments, with instruments measuring in the water column, with instruments measuring in the surface, also using platforms of opportunity like ferry boats, and of course a very important component of observations made from space platforms. But measurements on their own are not enough. Then we need the models in order to combine the observations and produce the interpolation in space and time, and being able therefore to deliver a full map, not just point measurements or intermittent measurements. We need then to deliver all this information in real time, and this is the scope of operational oceanography: delivering data where and when it counts. Of course, keeping the importance of data in the sense of enabling us to manage. We cannot manage what we do not measure. Just to give you an idea, I'm showing you here one of the operational systems that we have in Malta. Of course, other countries have more than we can offer, but I like to show you here that even in Malta we have some operation and oceanography activities. And first and foremost, for example, this model, this is the Rosario forecasting system. You can access the current operational version of the model through this URL address, and it gives forecasts. It gives forecasts and added value products to our users. And I wanted to show you this as an example, only a simple example of what can operational oceanography produce. But we are here showing. We are here showing information to our users in the form of maps and animations, showing information not only at the surface but only at different depths. This is, for example, salinity at a depth of 180 meters. So I mean, if you go into the system, you can show the details of what operational oceanography can provide. This is only physical data, namely currents, sea temperature, and salinity. But there are other models which can provide many other information, but also added value information. This is further interpreting the data of the models, for example, by providing divergence maps. These are very useful also, for example, for fisheries, because these kind of maps show where we have water departing or water converging where it's red, water departing or diverging where it is blue. And as you can see here, for example, a current with the coast on its right is an area of convergence, whereas currents with the coast on the left in the northern hemisphere is an area of divergence. And convergence and divergence zones are very important because they are also related a lot with biological activity in the sense of, for example, an area of divergence is an area where new water comes from below, bringing up with it nutrients and therefore improving and increasing primary production and therefore really important for fisheries. So, I mean, these are the kind of products which operational oceanography can deliver. I don't know whether there are any at this stage before I continue, Audrey, whether there are any particular questions which you think I should address.
Not yet.
If there are any of the participants wishing to also speak out or make a question at the stage, because at the stage I've finished the first chunk of the. Before going to the next chunk, I'm ready to take a couple of questions if you have any, even related to what I was explaining before. Also, perhaps mentioning whether this was something which you already knew, but you have some further insight. It's good to have some interaction with you. If not, I will continue with the rest of the slides and go to the second part of the lecture. And I have here a few slides because they are all related to data interpretation. And this is very important. Probably very few people tell you about these things, but I wanted to include them in my lecture. This is about warning you against misinterpretation of data. And I can tell you that there can be a lot of misinterpretations when using data. I'm trying here in the coming slides to pinpoint, to enlighten you a bit about these possible fallacies that you can obtain from misinterpretation of data. First and foremost, I would like to tell you about the repeatability of measurements, okay? With the same instrument, in the same place, with the conditions remaining constant, using the same sensors. Would you obtain the same reading when you do it the second time, when you do it the third time? Okay? And the answer is not exactly so. We speak of, in fact, as you can see in this histogram here, when you repeat a measurement with constant conditions, even with constant conditions, and with the same sensor and with the same method, you always get a range of values. Of course, you try to keep this histogram very sharp, very narrow. That is, your ideal would be to have just one line, okay? So that all measurements are all repeated every time. But in reality, you never get this, okay? What is important is that when you do the measurements, even though there is a spread in the measurements, what's important is that the value, the mean, is accurate in the sense that it gives you the correct reading. In this example, as you can see, the mean is not exactly the value which is the correct one. There is a bias. And this is what we want to eliminate. It is allowed to have a span of measurements around a mean, but it is important that this bias, that this difference from the reality is kept as small as possible. And this is what we speak about: accuracy and precision. When we speak of an accurate measurement, we speak of a measurement which gives you the right value. When we speak of a precise measurement, we speak of a measurement which is easily repeatable. And therefore, if you look at this example here, this is both accurate, because the values are all around the correct value, and precise, because all the repeated values are very close to each other. This is the ideal, okay? This is the ideal. We're measuring accurately, because we're measuring the right value, and precisely. The repeated measurements are giving us always very similar values. But we may have situations, and you need to be aware, you need to be cautious about this, because if you do not understand that your measurement is not accurate, then you must not rely on your measurements before you know their quality. And as you can see here, you may have a very precise measurement. I mean, your instrument is still giving you very close repeated measurements, but all of them are out, biased, away from the truth. And this is very often the case. And when you have, in fact, as I'm showing you here, an instrument may drift in time. You see the difference between the two, these are two sensors measuring the same thing. But one is measuring the correct values, the other one has a drift. This one has a drift. And therefore, it introduces a bias between what you measure and the reality. And this is the example of a measurement which is precise, but not accurate. You can also have the situation where an instrument is on average giving the right result, but there is a lot of spread in your measurements. And therefore, this is an example of an accurate but not precise measurement. Or you can have, this is the worst scenario, you can have both inaccurate and non-precise measurements. And this is the worst case you can have. So I mean, be cautious. Before you use your data, before you deliver your results, make sure that your data set has the quality. Okay? It must be accurate, but not only, also precise. I hope you understood. I think this picture is quite expressive in sense it tells you exactly. Another aspect, speaking of data quality, I think you are all aware of certain data quality checks. Some of these are very simple, such as, for example, the spike, detecting the spike test. If you have some values which are very much away from the rest, especially when you have a successive measurement and the measurement is very much different from the previous one, that is indicative of a spike. And spikes are often eliminated from the measurements, otherwise they will alter the overall analysis. Or measurements which are out of range and therefore indicating an anomalous value in your data set. You need to remove these anomalies before you start doing the analysis. And therefore, I am referring here to the need of quality checking your data before using it. You must remove these inaccurate values from your data set before you start, because otherwise they may very much skew your results. But on the other hand, I want also to speak about these checks as important applications, such as, for example, in fraud detection. Giving you an example, PayPal, PayPal is one of the paying, one of the systems to pay when you buy online. But they have a machine learning powerhouse when it comes to fraud detection. And what they do is they apply time series analysis, like the one I was explaining, to track the normal frequency of operations of an account and trying to detect irregular spikes in the number of transactions. Such spikes, such findings can be checked against other suspicious activities like recent changes in the shipping address or massive funds withdrawal, and enable to highlight a given transaction as likely being fraudulent or not. So I mean, these kind of tools that we use for data quality in oceanography are also useful in other applications, also in cybersecurity purposes, to capture malware attacks. keeping a record on checking, an ongoing checking of data related to a service is also important to capture anomalous activity. Also, these kind of tools in predictive maintenance. This is about forecasting machinery failures. This is very important because if one can anticipate a failure before it actually happens, then this will reduce downtime and reduce costs. Therefore, and there are tools that enable subtle anomalies in the current sensor readings in order to detect changes in the system that indicate possible future failure, and therefore anticipating before. So I mean, you see, the same tools that we use in our projects can also have many other different applications which are useful for many other different results. Data capture fallacies. What do I mean here? The way we measure, the way we collect the data, we need to have a warning on this as well, because we may collect data which is not able to stick to important data capture trends. I'm mentioning here 3 important aspects that may lead to wrong data, okay? One of them is choosing an incorrect sample of the population. What do I mean? Simple example, you're doing a survey, say a street survey, to find out about, say, the opinion of people on some aspect, and you only sample male persons or only female. That would be an incorrect sample because it may lead to bias, because gender point of views may be different, and therefore if you have a survey of this kind, you need to cater for both male and female together. So that would be an example of choosing an incorrect sample, okay? But also making measurements that are under a controlled situation. I don't know, for example, doing a survey and there is no anonymity, or doing a survey after making an intervention that would bias the responses. This is incorrect, you know, because the assessment that you make is biased because of your controlled intervention, or incorrect sampling. Taking an example from the sea again, for example, measuring only in one phase of the tidal cycle. If you are measuring in a tidally dominated domain, well, you have to be cautious to sample at different phases of the tide. Or measuring only in calm weather, of course, that would be biased, because you need also to measure when there are different conditions, or measuring only in summer, okay? Or and therefore sampling sampling only when the boat is available or the crew is ready to go at sea. That is not correct. You need to have a sampling strategy which is really taking all the aspects, and therefore you can easily have a data set which has this kind of bias, and therefore it's also important when you are using a data set, it's also important to assess how it has been collected, because that may make all the difference. So I wanted to put you on the watch out on this. And now a slide on data interpretation fallacies. Again, these are things which nobody may tell you about, but they are really, really important. Cherry picking is in fact about selecting results, you know? it is amazing how, for example, our politicians interpret the same data in completely the opposite, different way. Why? Because they only choose the results which they want to hear about, you know? And sometimes people writing their research results can also have this temptation, you know, of selecting only the results that match their claim, excluding the other results which do not fit the idea. And therefore, this is cherry picking, selecting only the results which fit to what you want to show, you know, that is incorrect. You must use the whole data set and interpret all the results, even if they apparently are against a common result. But also working only on a small subset of a data set. You see, I'm showing an example here of, say, sea level. And you choose a couple of years, and this is showing a trend. But in reality, if you look at the bigger picture, if you look at the whole data set extending over more years, this is part of a cycle, of a longer term cycle. And this is a very, very common mistake, namely to interpret results based on only a subset of the data, and therefore excluding the rest, and therefore excluding the reality. But there are other instances where data interpretation can lead to false results. For example, this is what is called data dredging. Misuse of data analysis to find patterns, trying to find patterns, that is, where they are inexistent. Example, wrong correlations. For example, trying to understand, I don't know, why the number of elephants in a forest are decreasing, and trying to associate to climate change without including the fact that hunting might be the major reason. And therefore, there may be a correlation between climate change and number of elephants in the forest, but the correlation is not based on real impact. The real impact is the hunting. And therefore, a correlation is not necessarily an answer. This is the point. Okay? But also, and this is also a very, very interesting aspect. I do not have it on the slide, but the way we report results, this can also have an impact on the interpretation of the results. Let me give you an example. A survey among scientists. 10,000 scientists have been consulted, whether they believe in climate change or not. And 99% believe in it. 99% of 10,000 is 9,900. The rest, 1%, is 100 scientists. But those who have the intention can report this by picking only on those 100 scientists who disagree and sending an alarming message. 100 scientists do not believe in climate change, without reporting that 9,900 believe in it. So I mean, it's true, 100 do not believe, but then there is the biggest majority who believe in it. So giving the impression by delivering only part of the story, you know, only part of the results, that is also very much related to misinformation. And I hope that by these examples, I'm putting you on the watch, but also from your end, be aware, because I'm showing you here an example. I think it's an interesting one. This is an interesting one, in which grouping of data can lead to different results. And I'm giving you here a very simple example. By the way, this is called Simpson's paradox, if you want to read about it. But I'm giving you here an example. These are the results between male and female of two subjects, of two exams. In one exam, 14%, that is 168 out of 1,200, passed. 50% of female passed, 270 out of 1,000. So the female did better in subject one. Even in subject two, the percentage, 400 out of 800, 50%, and 102 out of 200, 51%. Again, the female did better than the male. If you consider the subjects on their own as two groups, the female are performing better than the male in both. But if you combine them together, which would probably make more sense, if you combine them together, 568 out of 2,000, 28% of male passed the exam, and only 19%, 272 out of 372 out of 2,000. So I mean, which is the correct interpretation? Of course, both. But if you restrict to the grouping by subject, it's not enough, because you need also to group by the overall performance. And this is a very interesting example to show how grouping of data can lead to misinterpretation. Okay? And as I said, this is called Simpson's paradox, and you can read more about it. Also, this one is interesting. This is a common analysis that we do with the data. We measure two parameters, X and Y, and then we see how they are correlated. And we try to fit a model to it. And I'm here showing how the same data, this is the same data in 1, 2, and 3, exactly the same data, but we can fit different models to the same data. This is a simple linear, this is a quadratic, this is a more complicated fitting exercise. Which one should I adopt? We must be cautious not to use a very simple model, because a simple model may not be representing our data set sufficiently well. But we must also be aware against overfitting. This model may fit well the current set of data, but when we do another set of data of the same two parameters, it may not fit again. So we need to have a balanced model, upon which we can rely even when we do further measurements. And therefore, putting you on the alert against using too much complicated models to fit your data. That doesn't have any meaning. The model must fit also for longer data sets in order to be effective and useful. And therefore, warning you against using excessive sophisticated tools. If you can stay simple, it's better for a good interpretation rather than another danger. The fact of basing only on statistics. This is showing here 4 data sets which have the same mean, have the same variance, and therefore, unless you plot them, unless you see their shape, you wouldn't understand just from the statistics that they are different. So this is again another very important aspect to take into account. Those who rely only on statistics must be aware that, look, the same statistics may have data of completely different shape. So you cannot rely exclusively on statistics. Statistics on its own doesn't work because it may hide the real significance, the more deeper significance in the data. With this, I think I've explained most of the tricks that you need to be aware and the risks that you need to eliminate from your data analysis. I don't know whether there are any questions at this stage, but I hope that you appreciated these slides. I think they are interesting because they are putting you putting you in a position to understand better. Okay, when you do an assessment, you need to be very cautious. When you read the results of other people, you must be cautious that they have not done these they have not done these mistakes.
We have a question, Aldo.
Here, which is
In terms of data quality checks, how can these anomalies that have to be removed differentiated from events that have to be taken into account?
well, that is an important interpretation, huh? I mean, before removing a spike, you must be really sure that it's a spike related to a bad measurement, okay? Because a spike can also be a reality. But I mean, an experienced scientist would know, because I mean, if I am measuring during a calm day and I get a high significant wave height, I know that it must be a problem with the sensor. You cannot have just one instance where the significant wave height, okay? But on the other hand, if I am measuring during a storm, or if I am measuring during an event, in the sense of comparing with other data, if you have only one data set, it may be not enough. If you are in doubt, okay, whether a value is a spike or not, you need to also refer to parallel data sets, either taken by another sensor. If there is a spike, it will also appear on another sensor, okay? Or else by comparing to another parameter, because a spike may be also related to and also show up in another parameter. So yes, there are ways and means. First and foremost, experience, but also by comparing with other data sets. Does that answer the question? If there are no other questions, I don't know whether you want to take a short rest.
Aldo, he said yes, it answered the question. Thank you.
Okay, thank you. Shall we give them a 1-2 minute rest, Audrey?
Sure.
What time is it? How much did we spend so far?
It's 5 minutes past 6 almost.
Okay, 1 hour. Okay, let us stop 1-2 minutes and then we resume. Okay, let's give them a bit of a rest.
Okay.
Shall we start again, Audrey?
Okay.
Well, I hope you've had a short rest and refreshed a bit your mind, but we're more than halfway through the lecture in reality. But now I come to this slide, which I wanted to share with you because, today many people speak of innovation, of intelligence. They wanted to say a few words to you to perhaps enlighten you a bit of what do we mean by innovation, because I think very many people think that innovation is a breakthrough, is something which is completely new, something which nobody has thought about it before, whereas in reality, it's not that. And in fact, I'm showing you here. An innovation can be like a difference in a recipe. That is also innovation. I mean, you have a product which is composed of A and B, producing a product C. But a change in the ingredient, you see this one, a change in the ingredient, or a change in the process, instead of adding, subtracting, or adding a third ingredient, or a completely new recipe. These are all aspects of innovation. And therefore, innovation is not necessarily something completely new, but also something which is exploiting existing knowledge and transforming it into something new. That is also innovation. And I wanted to share this perspective to you, so that you understand. This is also part of the course, widening your knowledge. And in fact, this is what I am showing here, you see. We collect data. We add to it a lot of information, which may not necessarily be only scientific, but data and information feeds knowledge. With data and information, we learn, and that increases our knowledge about a system, whatever it is. And of course, you need skill in order to transform data and information into knowledge, okay? But then, with additional knowledge, we can create innovation. And again, this step requires a lot of skill. The point of showing this is also to highlight that, well, this is a process. You cannot have innovation between knowledge, before you have knowledge and before you have data and information. So this is a process. And this process is not necessarily the result of one person. We always, and this is how research should be, we always build upon the results of others, okay? And this is what makes our endeavors in research more efficient, being able to use what others have done before us in order to give either different interpretations or to improve. What is important, however, is this whole process is what results in competence and excellence, and therefore what results in what and how we define our intelligence. And I want to here refer to the fact that professionals need to really acknowledge what others have done before them, okay? There are, and I really dislike those people who make their own what others have done before them. I really like to instill in you the professionalism of being able to, first of all, rely on the legacy provided by those before you, but also to recognize it. You must not make your own what others have done before you. Okay, and I really want to stress on this point. This is what will make you eventually the real, true professional researchers, and what will gain your real reputation. Okay, I hope that you take this message. Now I want to go into the next slides, where I will be explaining some other important things about data. Mainly, I want to describe to you what we mean by a climatology, because I am aware, sorry, I am aware that even with professionals, sometimes you go to stakeholders and provide them with information, and they do not, and they are not able to interpret it. They are not able to understand it, not interpret, to understand it. And first and foremost, there are many professionals out there who are working even at important positions, and they do not realize exactly what is meant by a climatology. I want to spend some slides explaining to you, because I think this is a very essential, important thing to know about. Okay, um, and in order to give you an example of climatology, I would like to introduce you to a service that we are doing. This is a completed service in its first phase. This is the link to the project which has produced this service. If you go to products on this web service, on this website, you will find a web app which gives a lot of important interpretation of existing data in the area of the Maltese Islands, of course, in this case. But this application is also available on a mobile app. And on this slide, you have here the QR codes, whether you are using an Apple or an Android smartphone. These are the QR codes which can allow you to go into and subscribe to the system free of charge. Yeah? I will not go into the details of telling you what it is and how it works, only to say that this is an innovative application where we allow the user to see only and to extract only the data which he needs, instead of giving, as I showed before, a map. And that same map is delivered to all the users. We deliver here only the data that the user is requiring. So if a user is a fish farmer and wants to have data only where he has his fish farm, this app is available to give him the data, that the personalized data that he wants. But the intention is not to tell you more about this, but only to showcase how within this app there is data which I am taking in order to explain to you what we mean by climatology. Okay, so these pictures that I'm showing you are all taken from that app. And what am I showing here? I'm taking an example of sea surface temperature. Okay, but what I'm saying for sea surface temperature can apply for any other parameter. Okay, this is showing here in blue. In blue, I have the time series from January to December. That is for a full year. For 40 years. Okay, in blue, we have 40 plots, all upon each other. Okay, showing how the temperature changed over each of those years. And as you can see, if you look at the blue plots, they all follow somewhat the same pattern. Low temperature in the winter months, of course, and high temperature in the summer months. But the important thing to notice is that there are sometimes very different values from year to year. This is an important aspect to learn and to understand, that even if you are measuring the same quantity, sea surface temperature in this case, it doesn't repeat exactly from one year to another. Okay? So if it is the 15th of August of this year, you will not expect the same temperature to occur again the next 15th of August the following year. And this is what I am showing here, you see? All these plots are showing that you can have many different variations in temperature, okay, following the overall path or the overall pattern. The one in red is showing the last year of interpretation, the last year of sea surface temperature. When we did this exercise, it was 2023. So as you can see, it was a year where we had a very high temperature in July, okay? But it doesn't mean that it was always as high as that in the previous years. But when you consider all of these data together and you take the average, this is what we are showing in black. The average, okay, is the average over the 40 years. This is the plot shown in black. And this is the mean climatology. When we say the mean climatology, it is taking into account the variability along the 40 years, but taking an average. And if you want to know what temperature to expect next year, it is the climatology which can tell you, not the temperature of last year, because that may be anomalous, you see? So when you read, and this is also what we do with atmospheric data, when you are traveling and you want to know what climate or what weather to expect when you travel to a place, and whether in the equator or above or below or wherever, you need to look at the climatology, but because that gives you an idea of the expected range. And a climatology may not necessarily be only the mean. There are also other quantities which are accompanying a climatology. And this is what many people do not understand. They understand the mean, but then they do not understand that the climatology has more than just the mean. It has also the maximum. The maximum is the highest temperature ever measured, or the minimum, the least, the lowest temperature ever measured over that particular period, in this case of 40 years. The maximum and the minimum are also part of the climatology. And then there are also the percentiles, very typically the 90th percentile and the 10th percentile. These are two very common, important climatological measures. The 90th percentile is that temperature expected to be lower 9 out of 10 times. So that if the 90th percentile is, say, for example, 27 degrees, 9 years out of 10 are expected to have a temperature lower than 27 degrees. This is the meaning of the 90th percentile. I'm not showing it on this plot, but I will be showing it in the next slides, okay? Whereas the 10th percentile is that value 9 out of 10 times expected to be higher. So if the 10th percentile is, say, 16 degrees, okay, it means that 9 out of 10 times the temperature is expected to be higher than 16 degrees. So this is, first of all, what I'd like you to understand about the climatology. A climatology is built from data over a number of years, at least 20. If you have more, it's even better, because it gives you a better picture of the variability. We need a climatology because the climatology is not only the mean, the climatology must also give the expected variability. Okay, the mean on its own is not enough. You need also to know how much you are expecting above or below the mean. And this is why we also include in a climatology in the 90th percentile and the 10th percentile. The 90th percentile is a value that gives you an idea of how much is it expected to be higher than the mean. The 10th percentile gives you an idea of how much it can be expected to be below the mean. And then there is the maximum and the minimum, which give you the overall extremes. I hope that with this picture, you are understanding exactly what we mean by a climatology, and also what kind of analysis you need in order to work out a climatology. So first of all, you need at least monthly averages over a number of years, okay? Sorry, not monthly, daily values, in this case of sea surface temperature, over a number of years. So if it's 40 years, I have 40 values for 1st of January, 40 values for 2nd of January, 40 values for the 3rd of January. And taking day by day, you can calculate these 5 quantities, okay? For each day, over 366 days. And that is what makes the climatology. Climatology is, in fact, 366 days, okay? Including 29th of February for leap years. So I hope that you got an idea of how you work out a climatology, okay? You need all these data, daily values over a number of years, in this case, 40 years. And now I can go to the next slide. If you use the mobile app that I mentioned before, you can view point by point. So this is a picture, so it's not interactive, but if you are using the app directly, you will be able to view the values wherever you need. But just to show you that a climatology around the Maltese Islands for sea surface temperature is not just one value, because the climatology varies from point to point. So this is showing, for example, the climatology around the Maltese Islands for sea surface temperature on the 7th of March. Each point, okay, is showing the mean over 40 years. Sorry, in this case, I'm plotting here the maximum. Each point is showing the maximum, but you can look at the same maps for minimum, for 90th percentile, for 10th percentile, and for the mean. And therefore, making the point here that a climatology is not a single value each day for the whole area, but you can work out the climatology pixel by pixel. And this is what we have done in this project, and this is what we are providing in this mobile application. We're providing all this data in the hands of the users, namely showing point by point the climatology for the sea surface temperature around the Maltese Islands. And you can select 7th March, or you can select any other day of interest. So I hope that with this, you understand what we mean by a climatology. And why is a climatology important? Because if you know a climatology, you are also able to calculate the anomaly. When you say anomaly, for example, if the anomaly at a certain point, let's just concentrate on this point, okay? And the anomaly, I mean, if you are on the app, it will tell you the value directly. Here I'm showing it on a color bar. But I mean, if you click on it on the mobile app, you will get the anomaly. And what does that anomaly mean? If it is 3.5, it means that the temperature on that day, this is the 11th of September of 2024. I chose this as an example, but it can show you the SST anomaly on the day, or even for today. In the mobile app, it is updated every day. But I mean, I'm showing this just to make you understand. When we say then an anomaly, what does it mean? It's the anomaly is the difference between the measured temperature on that day with respect to climatology. So this map is showing me point by point how much is the sea surface temperature measured on the 11th of September of 24 different from the climatology. Okay? So this is what we mean by the anomaly. The anomaly is the difference of the observations of the current value of the particular parameters, the surface temperature in this case, with respect to climatology. So this is why a climatology is very important, because if we know the observations and we know the climatology, we can obtain the difference between the two, which gives us the anomaly, which can be either positive or negative. You see here, the positive anomalies are in red. The negative anomalies are in blue. So these areas are areas where the anomaly is negative, and therefore the measured temperature is below the climatology. Whereas there are other areas, such as around the Maltese Islands, where for this particular day, the temperature was higher than the climatology. And this gives you an idea of where we have the excess temperatures, okay, where the anomaly is large. It means that we are more outside the norm, okay? And we can visualize this day by day by using, in this case, sea surface temperature obtained from satellite. We can also focus on a single point, and this is um, data for a single point, which the user can select. This is a single point from the 13th of August to the 20th of September of 2024. And we are showing here the observations. These are the observations for this particular point. This is a point, I forgot which latitude and longitude it was, but it was a point near the Maltese Islands for this period, okay? So this was summer in 2024, last year, between the 13th of August and the 20th of September. And we are measuring here the temperature, the sea surface temperature. The values in blue, okay, are the sea surface temperature measured at that point. We are also giving the forecast. And we are comparing, this is what is important. We are comparing day by day with these values. You see, the red here is the mean climatology, the expected temperature according to the climatology. This one in red is the expected 90th percentile, shown here. And this one in green is the 10th percentile. So this is showing the climatology, how it is expected to give the variability day by day, okay? Giving for each day the mean, the 90th percentile, and the 10th percentile. But then on top, we have the observations, the actual measurements. And the difference between the measurements and the mean, you see this line here in red, this is the anomaly. This is the anomaly. So it is showing very interestingly that during last summer, for this period of time, and in fact for most of the time, we always had a positive anomaly. That is, we are experiencing throughout summer higher temperature than expected according to climatology, okay? Then there was an event starting from the second week of September, where wind and a storm that occurred cooled the sea temperature, and we started to get negative anomalies for the rest of the days. But the point to make here is that with these tools, we are able to assess quantitatively in numbers how warmer or cooler is our sea surface temperature with respect to climatology. And this gives us a measure of the stress on the marine ecosystem. And in fact, this is my next slide. It is showing here how we measure the stress. This is the climatology. But the actual temperature can be higher, category 1, or even higher, or even higher, or even higher. This in dotted line is the observations. I'm giving this as an example, showing that this is following a methodology, first elaborated by Hobday in his paper in 2018. And this is what we adopt to measure the category of the excess heat, what we call as a marine heat wave, whether it's category 1, category 2, 3, or 4. And this is measured by considering the difference between the observation and the climatology. Okay, so on this day, it was category 2. On this day, it was category 3. On this one, it was category 4. Okay, it's about how much is the anomaly fitting in these ranges of moderate, strong, severe, or extreme, according to these definitions. The point is that with the climatology and observations, in this case from satellite, we are able to produce these maps. This is a map of the severity of a heat wave. Okay, where it's white, it means there is no excess temperature with respect to climatology. Where it's yellow, it's moderate. Where it's brown, it's strong. But we can also have instances where the marine heat wave is much higher. And we produce these maps every day, which you can access from this mobile app that I mentioned. I'm showing this as an example, okay, to show you how a climatology is defined and how a climatology is used to make assessments. I hope that you find this interesting, but in reality, it is a service which you can view on our mobile app. Of course, only for this area. This is not an app covering the whole MAD or larger. It is a prototype for our area, but it is it's showcasing how these kind of data can be interpreted to provide useful products, useful information to our users. And now I conclude very quickly with my last slides. I hope you are enjoying this lecture and you are not tired. But I will not take much longer now because. But I would like to end my lecture showing you also this aspect of data analysis, namely to explain to you that when you do a time series is always composed of many signals together. I'm showing here a very simple example where, as you can see, the time series is composed of two signals. It's composed of this signal and this higher frequency signal. And if I look at the spectrum, as I'm showing here, the spectrum has two peaks because this time series, this measurement is made up, it's a composition of two signals added together, okay? A high frequency and the lower frequency signal, resulting in this combined signal. In reality, things are much more complicated because in nature, it's not just 2 or 3 signals which are adding up, but in reality, very, very often, and I'm taking here an example of this of sea level. When you measure sea level, this is a combination of many factors. The sea level measured is an addition of the astronomical tide, of the meteorological forcing, of the seasonal cycle, of the long-term changes, of local effects. So when you are measuring sea level, the overall time series is complicated. It's a combination of many signals, but not only in marine research. This is also in other instances. I mean, if you have, for example, data related to export, the export rate is based on currency exchange, time of the year, transport costs, staff costs, and perhaps other factors. It's a combination. When you assess and you try to interpret a time series of export rates as it evolves over time, there are many factors which compose its variability, okay? Like sea level. And this is what I wanted to explain to you, namely that when you are measuring something, okay, let us stick to sea level in this case. But what I'm saying applies to everything else. You must understand that the overall measurement that you are measuring, the variability, okay, in time and in space, is a result of many different signals. And when you are going to analyze, you must be able, as much as possible, to interpret the signals that you want to measure. And this brings us to a very interesting question, okay? When you have an instrument and you want to measure, let's say, sea level, just to stick to the same parameter, okay? and you have an instrument and you want to set it up to measure sea level. But then the basic question comes to decide which sampling to adopt and how long. If you are doing sea level measurements, how long should I measure? Okay, 1 year, 2 years, 30 years, just a month? What criteria do you use to give an answer? Okay? And also, what time interval? That is, how frequently should I measure? Every minute? Every hour? Every second? You may say every second, because that's the best. It gives you the maximum. But if you're measuring every second, then this will be at the expense of the capacity of your power supply, for example, or how much your sensor is capable to measure that frequently. So I mean, there has to be a compromise, you know, between how long and how often you measure. And when you come to make these decisions, it's important to have some background about how to interpret what you want to measure. And this is what I'm showing in my last 2 slides, giving you some idea of how you do these kind of decisions, okay? How long am I going to measure? And how often am I going to measure? And these slides that I'm showing are exactly telling you the answers. How long? This is telling us how long do I have to measure? It depends on which signals you want to measure. As I mentioned, the overall measurement is a combination of signals. So in sea level, there may be signals that have a shorter time scale, but there may be signals that can have a longer time scale of the order of years. If I'm only interested in the short time scales, or if I'm interested in the longer time scales, then my decision on how long to measure will be different, in the sense that, as I'm showing in the slide, the overall period of measurement depends on the period, on the time scale, that is, of the signal that I want to measure. If the signal has a time scale t, say 1 year, then I must measure for at least half a year. If the signal in which I am interested is of the order of 10 years, then I need to measure for at least 5 years. This is always the rule to adopt, okay? You cannot resolve a signal with time scale t unless you have at least t on 2, unless you have a span of time, at least t on 2 of measurements. I hope you understood this, and I go now to my second slide on this aspect. And how often should I measure? This is again depending on the kind of signals you want to resolve. If you want to resolve signals of the order of 2 minutes, then you should at least measure every half of the order of 2 minutes. Then you should measure at least every half a minute. It's always take the shortest time scale, and the sampling interval should be at least half or less than that amount. So if I want to resolve higher frequency signals, of course, I need to measure more frequently. And the rule is exactly this one. The sampling interval must be at least equal to half the time scale that I want to measure. Okay? So with this, I think I gave you some important criteria to use. And finally, the slide, this is my very last slide. If I have a time series spanning over a number of years, perhaps, how should I tackle the analysis of such a time series. Should I take it? This is often a common question, you know, made by students. Should I take the whole time series as a whole, or shall I take a running window, starting with, say, a section, then moving on to an overlapping section, then moving on to a third overlapping section, and therefore analyzing over a running window uh, of, of data sets? And the answer, well, again, relies on what you want to achieve. Very often you do both things, because if you consider the whole data set as a whole, as I'm showing in this arrow, you see, if I consider the whole data set as a whole, it means that I can cover more timescales. Okay, and therefore I can find longer term patterns. I can understand longer term patterns if I take the whole data set together. Whereas if I take section by section, then I will have better resolution in frequency. That is, I can see more resolution in the finer timescales. And therefore, again, the data analysis that you do depends on the result that you want to investigate. And I think with this one, this was my last slide. Those of you who would like to keep contact with me or to make questions, or this is my personal email address, and I would be very glad to have also some responses from you. I stop